Welcome to this coding challenge walkthrough. In today's session, we will explore problem number 764, titled Largest Plus Sign. This problem involves algorithmic thinking and optimization strategies to find the largest plus sign in a grid. Let's dive in and break it down step by step. In this problem, you're tasked with working on an nxn grid. Initially, every cell in the grid contains A1, but we are also given a list called mines. Each mine is a pair of coordinates, x, y, and it represents a cell in the grid that is set to 0. Now, the goal is to identify the largest possible plus sign that can be formed in this grid. What exactly is a plus sign? It's a pattern where there is a central cell, and from this center, there are arms of contiguous 1s extending outward in all four cardinal directions, up, down, left, and right. The length of each arm, including the center, determines the order of the plus sign. To summarize, we want to compute the order of the largest plus sign that can be formed, and if no plus sign can be formed, the result should be 0. The output of this problem is a single integer that represents the order of the largest plus sign in the grid. To better understand the problem, let's look at an example. Consider a grid of size n equals 5, and we have one mine at position 4, 2. This means the cell at row 4, column 2 will be set to 0. After placing the mine, the grid looks like this: all cells are 1 except for the mine, which is 0. The largest plus sign in this grid has an order of 2. This is because the longest arms of 1s extending in all directions from the center of the plus sign are of length 2. Any larger plus sign would encounter the 0 cell and break the pattern. Now let's examine another example. If n equals 2 and there are no mines, the grid remains completely filled with 1s. In this case, the largest plus sign has an order of 1. This is because the arms of the plus sign can only extend to the edges of the grid. Since the grid is so small, the plus sign is limited to its center cell and no longer arms. Even though there are no mines, the size of the grid restricts the size of the plus sign. In a final example, suppose n equals 1 and the only cell in the grid is a mine. The grid now consists of just a single cell with a value of 0. Here, no plus sign can be formed because there are no 1s in the grid. Therefore, the output in this case is 0. This example highlights the importance of the mines. A single mine can completely prevent any plus sign from being formed in very small grids. To summarize the constraints, the size of the grid, n, can range from 1 to 500, and the number of mines is limited to a maximum of n-2 or 10,000, whichever is smaller. Each mine is guaranteed to be within the bounds of the grid. Some important edge cases to keep in mind include scenarios where the grid has only one cell and it's a mine, where the output will be 0. If there are no mines at all, the largest plus sign will be determined by the size of the grid, specifically the maximum order that can fit within the grid's dimensions. Finally, if all cells are mines, the output will also be 0 because no plus sign can exist under those conditions. To begin, let's consider the brute force approach to solving this problem. Here, we iterate over every cell in the nxn grid. For each cell, we calculate the size of the largest plus sign centered at that position by expanding outward in all four directions, up, down, left, and right. The expansion stops as soon as a mine, represented by a 0, is encountered in any direction. The size of the plus sign for that cell is then determined by the shortest distance it can expand in these directions. While the intuition behind this method is straightforward, the inefficiency becomes apparent when we analyze its time complexity. For each cell, we potentially scan entire rows and columns, leading to a cubic time complexity of n cubed. Additionally, this approach uses no extra space, making its space complexity 1. However, the major drawback is that it involves a significant amount of redundant computation, especially in larger grids, as the same rows and columns are repeatedly scanned. This inefficiency makes the brute force solution impractical for large-scale inputs. Now, let's explore the optimized approach that leverages dynamic programming with pre-processing to address the inefficiencies of the brute force method. The key idea is to pre-process the grid and calculate the maximum possible arm lengths in all four directions, left, right, up, and down, for each cell. We achieve this by creating a DP table, dp, I, j, where each entry initially represents the largest plus sign arm length at that cell. The pre-processing is done in 4 linear passes over the grid. In the left-to-right pass, we calculate the maximum arm length extending leftward for each cell, then repeat similar computations for the right-to-left, top-to-bottom, and bottom-to-top passes. After these passes, the largest plus sign for any cell, I, j, is determined by the minimum of the 4 pre-computed values for that cell. This pre-processing eliminates redundant calculations and ensures efficiency. The time complexity of this approach is O, n squared, as each pass processes the grid linearly, and the space complexity is also O, n squared, due to the DP table. This method is a significant improvement over brute force, as it balances computational efficiency with clarity. The chosen strategy for this problem is the optimized approach using dynamic programming. The critical insight here is that the maximum size of a plus sign at any cell depends on the shortest arm length among the 4 possible directions. By pre-processing the grid in linear passes, we effectively eliminate redundant computations, making the solution both time and space efficient. While maintaining the DP table introduces some overhead, this trade-off is minimal compared to the substantial performance gains achieved. When comparing alternatives, the brute force method proves to be highly inefficient for larger grids due to its redundant calculations and cubic time complexity. On the other hand, the dynamic programming approach scales well to larger inputs, offering clear advantages in terms of both efficiency and practicality. This makes the DP-based solution the optimal choice, as it strikes the right balance between performance, scalability, and simplicity in implementation. The goal of this problem is to determine the size of the largest plus sign that can be formed in a given nxn grid. In this grid, cells are either 1 representing free space, or 0 indicating a mine. A valid plus sign is defined by a central cell with arms of equal length extending outward in all 4 cardinal directions. These arms stop when they either encounter a 0 or reach the grid boundary. To solve this, we'll start with a brute force approach, breaking it down into clear steps. First, we parse the input grid and initialize a variable called max_plus_size to 0, which will track the size of the largest plus sign we find. Then, we iterate over every cell in the grid, treating each cell as a potential center for a plus sign. If a cell contains a 0, we can immediately skip it, since a plus sign cannot exist there. Only cells with a value of 1 are candidates for further exploration. For each potential center cell that contains A1, the next step is to expand outward from that cell in all 4 directions, up, down, left, and right. For the upward direction, we start at the row above the center and keep checking cells directly above it until we either hit a 0 or go out of bounds. The same process is applied for the downward direction, checking cells below the center. Similarly, we expand to the left and right by examining cells in those respective directions until we encounter invalid cells. As we expand, we track the maximum length that the plus sign can extend in all 4 directions using a variable called arm_length. The key is to find the minimum distance among these 4 directions, as it determines the maximum size of the plus sign that can exist for the current center. Once we know the arm_length, we calculate the size of the plus sign by using the formula 2k plus 1, where k is the arm length. This represents the center plus the 2 arms. If this size is larger than the current max_plus_size, we update it. We repeat this process for all cells in the grid to ensure that no potential center is missed. A few key insights can help solidify our understanding of this approach. First, the arms of the plus sign must stop at cells containing 0 or at the grid's boundary, ensuring that the plus sign remains valid. However, this brute force method recalculates the arm lengths for every cell, which is inefficient. This inefficiency can be addressed in optimized approaches by pre-computing the maximum reach in each direction up, down, left, and right for all cells. Additionally, we need to handle edge cases carefully. For example, if the grid is filled entirely with 0s, the largest plus sign size is 0, as no plus signs can form. Similarly, very small grids like 1x1 or grids that lack space for arms require explicit handling. In terms of data structures, the algorithm primarily uses the input grid and a few variables, such as max_plus_size to store the largest size found in arm_length to track the current expansion. Finally, let's consider the complexity. For an nxn grid, we iterate over all cells, which is O, n squared, and for each cell, we potentially check up to n cells in each direction, resulting in a worst-case time complexity of O, n cubed. The space complexity is O(1), since no additional data structures are used beyond the grid itself. To solve the largest plus sign problem, we start by defining a class called solution and the method order of largest plus sign. The goal here is to calculate the size of the largest plus sign that can be formed in a grid, taking into account cells that are marked as mines. First, we initialize the grid with all ones, where each cell represents the maximum potential arm length of a plus sign at that location. The size of the grid is determined by the input parameter n. Next, the list of mines is converted into a set, which allows us to quickly check if a cell is a mine. This is important for optimizing access during the traversal. We then iterate through the grid to calculate the minimum arm length for each cell in all four directions: left, right, up, and down. For the left direction, as we traverse row-wise, we reset the count to 0 if the current cell is a mine. Otherwise, we increment the count and update the grid with the minimum value between the current count and the existing value. Similarly, for the right direction, we traverse row-wise but in reverse, starting from the farthest column. Here too, we update the grid based on whether the cell is a mine or not. This ensures that for each cell in the row, we have the minimum arm length considering both left and right directions. Next, we calculate the arm lengths for the up and down directions by traversing column-wise. For the up direction, we traverse from the top to the bottom of the column. If the cell is a mine, we reset the count to 0, otherwise, we increment the count and update the grid with the smaller value between the current count and the existing value. For the down direction, we traverse from the bottom to the top of the column, following the same logic. By the end of these iterations, every cell in the grid contains the minimum arm length from all four directions, effectively representing the largest plus sign that can be centered at that cell. Finally, to determine the size of the largest plus sign in the entire grid, we simply find the maximum value across all rows of the grid. This value is returned as the result, giving us the order of the largest plus sign that can be formed. Here, we start by setting up the grid and initializing it with the maximum possible value, which is the size of the grid, n. This ensures that every cell initially assumes it can be part of the largest possible plus sign. Next, we use a hash set to store the positions of the mines, making it efficient to check whether a particular cell is blocked. After that, we iterate through the grid row by row. For each row, we calculate the number of consecutive cells without a mine from both the left and right directions. The left variable increments continuously unless we hit a mine, in which case it resets to 0, and we update the grid cell with the minimum value between its existing value and the current left count. Similarly, for the right direction, we work backward from the last column, using the same logic to update the grid. This ensures every cell in the row knows the maximum arm length it can contribute in the left and right directions. Now, we handle the vertical directions, starting with the up and down arms. For each column, we iterate through the rows, keeping track of consecutive cells without mines in the up direction. If a mine is encountered, up resets to 0, otherwise, it increments, and we update the grid with the minimum value between the current up count and the existing value in the grid. Similarly, for the down direction, we iterate upward from the bottommost row, using the same logic to update the grid. After processing all four directions, each cell in the grid holds the size of the smallest arm it can extend, effectively representing the order of the largest plus sign centered at that cell. Finally, we iterate over the grid to find the maximum value among all cells, which gives us the order of the largest plus sign in the grid. This value is then returned as the result. To solve this problem, we start by initializing a grid of size 3 by 3, where all cells are set to the maximum possible arm length, which in this case is 3. This represents the largest potential plus sign order at each cell if there are no restrictions. Since there are no mines in the grid, the mines underscore set remains empty, meaning no cells are blocked. Next, we perform a row-wise traversal. As we traverse from left to right, we calculate the minimum arm length at each cell based on the current direction. For the first row, the values update to 1, 2, 3. Then, as we traverse from right to left, the values remain unchanged since the minimum arm lengths are already optimized. Repeating this process for the remaining rows gives us an intermediate grid where each row has values 1, 2, 3. We then proceed to a column-wise traversal. Starting from the top and moving downward, we update each cell by considering the smallest arm length in the vertical direction. Similarly, as we traverse from bottom to top, we ensure the minimum arm length is maintained. By combining the results of these vertical traversals, the grid updates further. For example, the first column becomes 1, 2, 1, as we consider the vertical constraints. After completing this step for all columns, the final grid becomes 1, 2, 1, 2, 3, 2, 1, 2, 1. This updated grid reflects the maximum possible plus sign order at each position, considering all directions. To determine the final result, we simply find the largest value in the grid. In this example, the maximum value is 3, indicating that the largest plus sign has an order of 3. For the next example, we analyze a medium-sized grid with mines placed at specific locations. Here, the input specifies a grid size of 5 by 5 with mines located at positions 1, 2, 2, 2, and 3, 2. We start by initializing the grid, setting all cells to the maximum possible arm length of 5. This initial state assumes no restrictions before we account for the mines. After initializing the grid, we update the cells corresponding to the mines, setting their values to 0. This creates blocked positions in the grid where no plus sign arms can extend. The updated grid now reflects these mine placements, with zeros in the appropriate cells. Next, we perform a row-wise traversal, as we did previously. During the left-to-right pass, we calculate the arm lengths for each cell while skipping over the mines. The right-to-left traversal ensures the arm lengths remain minimal for each direction. After completing this step for all rows, the grid is updated to show the influence of the horizontal constraints. Now, we turn to column-wise traversal. Starting from the top and moving downward, we update the arm lengths at each cell by considering the vertical constraints. Similarly, as we traverse from bottom to top, we ensure that the arm lengths remain minimal in all directions. Once completed, the grid reflects the final state after accounting for all constraints from the mines. At this stage, the grid clearly shows the maximum possible arm lengths for a plus sign at each position. By finding the largest value in this grid, we determine that the largest plus sign has an order of 2. In the edge case where all cells are occupied by mines, the process is straightforward. Here, the input specifies a grid size of 2 by 2, with mines placed at every cell. We begin by initializing the grid with all cells set to 2, the maximum possible arm length for this size. However, once we insert the mines, all cells are updated to 0, indicating that no plus sign can be formed. Since every position in the grid is blocked, there are no valid plus signs, and the maximum order is 0. With all cells blocked by mines, the final output for this edge case is simply 0. This result highlights the importance of considering mine placements when calculating the largest possible plus sign. By systematically updating the grid and applying constraints in all directions, we can handle a variety of scenarios, from grids with no mines to those fully occupied by mines, and accurately compute the largest plus sign order for any given input. To analyze the time complexity, we start by looking at the grid initialization. Since the grid is of size n by n, and we're filling each cell with an initial value of n, this step takes n squared time. Next, to efficiently check for mines, we convert the list of mines into a set. This involves iterating over all m elements in the mines list, which adds m to the time complexity. Now, for the row-wise traversals, we process each row individually. For every row, we perform 2 passes, one from left to right and the other from right to left, each iterating through n columns. This results in n time per pass, or 2n per row. With n rows in total, the row-wise processing sums up to n squared. Column-wise traversals are similar to the row-wise ones, but instead of rows, we process each column. For every column, we traverse from top to bottom and then from bottom to top, iterating through all n rows in each direction. This takes n time per pass, or 2n per column. With n columns, the total time for column-wise traversals is also n squared. After processing the grid, we need to find the maximum value in it. This is done by iterating through all n by n cells, which takes n squared time. Combining all these steps, the dominant term comes from the row-wise and column-wise traversals, each contributing n squared. Adding the smaller term m for the mines, the overall time complexity becomes n squared plus m, which simplifies to n squared, when m is relatively small compared to n squared. Now let's examine the space complexity. The largest contributor is the grid itself, which is a 2D list of size n by n, requiring n squared space. Additionally, the lines are stored in a set, which uses m space for m lines. Apart from these, we use a few auxiliary variables like left, right, up, and down to keep track of arm lengths in the 4 directions. Since these are scalar values and reused during iteration, their contribution to space complexity is negligible. Considering the dominant terms, the grid storage dictates the overall space complexity as n squared. While the line set adds m, it is typically much smaller than n squared, so the final space complexity remains n squared. Let's compare the brute force approach to the optimized solution. In a naive method, for each cell in the grid, you would explicitly calculate the size of the plus sign by traversing in all 4 directions until a mine is encountered. With n by n cells and a maximum traversal length of n in each direction, this results in n cubed time complexity. The optimized approach, on the other hand, uses pre-computed arm lengths for all cells. By combining row-wise and column-wise traversals, this method reduces the time complexity to n squared for the entire grid. In terms of space, both approaches require n squared to store the grid. However, the optimized solution uses an additional set for mines, which is minimal compared to the grid size. Overall, the optimized approach is significantly more efficient in time while maintaining similar space usage. To summarize, the optimized approach achieves a time complexity of n squared and a space complexity of n squared, making it highly efficient for larger grids. In contrast, the brute force method has a time complexity of n cubed and the same n squared space complexity, which makes it impractical for large inputs. By reducing the time complexity from cubic to quadratic, the optimized solution becomes well-suited for constraints where n can go up to 500. This improvement highlights the importance of leveraging dynamic programming to streamline computations in grid-based problems like this one. When tackling the largest plus sign problem, there are several common errors to watch out for. First, it's crucial to account for all 4 directions up, down, left, and right when evaluating the size of a plus sign at a given cell. Missing even one direction can lead to incomplete calculations, causing the algorithm to either overlook valid plus signs or overestimate their size. Another pitfall is the use of brute force, where you attempt to expand outward from every cell in the grid without optimizing the process. This can result in a time complexity of n cubed, or worse, which becomes highly inefficient, especially for larger grids. Additionally, edge cases are frequently overlooked. For example, if the grid contains no valid plus signs because all cells are blocked, or if you're working with single row or single column grids, special handling is required. Similarly, uniform grids, where all cells are either ones or zeros, can also lead to errors if not considered carefully. Failing to address these scenarios can result in runtime errors or incorrect outputs. Another common mistake is recomputing overlapping subproblems, which happens when directional lengths are recalculated multiple times during the process. This redundancy wastes valuable computation time and slows down the solution. Instead, pre-computing and reusing these values can significantly improve efficiency. Boundary initialization is another area where errors often occur. For instance, when calculating directional lengths for cells near the edges of the grid, improper initialization can lead to off-by-one errors. These errors might cause the algorithm to skip valid cells or miscalculate the size of potential plus signs. Ensuring that boundary values are set correctly at the start of the computation is key to avoiding these issues and achieving accurate results. For interview scenarios, it's important to focus on several key aspects when solving this problem. Recognizing patterns is critical, as this problem can be effectively approached with dynamic programming. Pre-computing the maximum lengths in all 4 directions not only reduces redundancy but also demonstrates an understanding of optimization techniques. Interviewers often look for candidates who can articulate why brute force solutions are suboptimal and instead aim for an n squared complexity. Using auxiliary arrays or in-place updates to achieve this balance is a great way to showcase your thought process. Additionally, handling edge cases thoroughly is vital. For example, you should be prepared to discuss what happens when the grid size is just 1 or when all cells are blocked. Being comprehensive in addressing constraints highlights your ability to think critically. Lastly, be ready to discuss the trade-offs between space and time complexity. For example, using auxiliary arrays can speed up computation but increases memory usage, whereas in-place updates save space at the cost of implementation complexity. This problem also shares similarities with others, such as the number of islands problem or maximal rectangle, which are excellent practice for grid-based algorithms. There are a few approaches to solving this problem, each with its own trade-offs. A brute force method involves expanding outward from every cell to determine the largest plus sign possible. While this approach is straightforward to implement, it has a time complexity of n cubed, making it impractical for larger grids. A more efficient solution uses dynamic programming to pre-compute the maximum lengths of consecutive ones in all four directions for each cell. By leveraging these pre-computed values, you can calculate the size of the largest plus sign in n squared. This approach requires additional space for auxiliary arrays, increasing space complexity to n squared, but it drastically reduces runtime. For even greater space efficiency, you can use in-place optimization, where the grid itself is modified to store directional lengths. This reduces space complexity to 1, but it comes with a trade-off: the implementation becomes more complex and harder to debug. Choosing the right approach depends on the constraints of the problem and your ability to balance space and time efficiency. Thank you for joining this walkthrough. Today, we tackled the largest plus sign problem using an efficient dynamic programming solution. Remember, pre-computing and optimization are key strategies in solving grid-based problems. If you enjoyed this session, like and subscribe for more content, and keep honing your coding skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!